Okay, so welcome everyone to this theory seminar. And today we have the pleasure to have with us Bruce Clarke from currently in Indria, but also still in Macquarie, or maybe not?
Yes, still
you will
still
tell
I'm a
us about
student.
that?
Officially, I'm still a student at Macquarie University. So,
Okay. And Bruce will be talking about a general framework for cofunctors. So please, Bruce, go ahead.
All right. Sorry about that. So yeah, before I get started, thank you again for inviting me to speak at this seminar. It's really good pleasure to be here. And secondly, apologies if I look a little bit wet. 15 minutes ago, I had to run through a massive storm to get to the building where I'm giving this talk. So that's why I may look a little bit wet. So today I want to talk about a general framework for cofunctors. And so this is really a culmination of a bunch of work I've been doing in my PhD thesis for the last few years. And so I guess the starting point is with some motivation. And I guess a phrase or a theorem that you may have heard at some time before is that a cofunctor is a morphism of polynomial comonads on set. And so this was originally proved by Denel Arman and Tamo Ustalu, who I think is in the audience. And so this is a really nice result. I like it a lot. And polynomials and polynomial comonads and so on have been getting, I guess, a lot of attention in the applied category theory community over the last couple of years, especially. And one of the things why cofunctors are so interesting from this point of view is that these polynomial comonads on set are actually equivalent to categories. And so we can see cofunctors as a sort of morphism of categories. And so I guess I'm an applied category theorist, but I'm also a category theorist in the pure sense. And I'm very interested in categories, and I'm interested in morphisms of categories. And I really want to understand what they're all about. And so when I look at this characterization or this definition of what a cofunctor is in terms of polynomials, there's sort of two main questions that come up for me, which motivate this talk. So the first question is, well, if this thing's called a cofunctor, surely it must be in some sense dual to a functor. And so how can we sort of really understand the duality between cofunctors and functors? When we look at this from the perspective of polynomials, it's not really so clear how we can do this and how we can see this duality. And so one thing I want to do in this talk is define some kind of nice setting where we can study both functors and cofunctors together. And so that's one question that's motivating us. And another question is, well, if cofunctors are morphisms of categories at the base level, then how can we sort of generalize this and define a notion of cofunctor between more general sorts of categories? So we might want to be interested in cofunctors between internal categories, or between enriched categories, or between multi-categories, and so on. And so, and again, from the polynomial perspective, it's not really super clear how we could get these more general notions of cofunctors. Sure, we can replace set by some locally Cartesian closed category and get some kind of notion of internal cofunctor, but maybe we want to work internal to something a bit more general than a locally Cartesian closed category. And so what I want to do today is sort of answer these two questions. And that's the motivation. And so if I just move to an outline of the talk, it's in four main parts. I want to start off with some history and give you some definition of cofunctor. And then the second part, I want to introduce this so-called double category of cofunctors and sort of talk about some of its nice properties. In the third part, I sort of want to introduce this general framework for cofunctors, and here we'll see that they're not only morphisms of polynomial comonads, but we can also see them as morphisms of any kind of monad we like, and we study these monads in the setting of double categories. And we'll look at several examples of how when we instantiate this in particular double categories, we get more general notions of cofunctor. And then finally, to finish the talk, I want to talk about how cofunctors can be used to talk about delta lenses, which is something else I've been looking at for a long time, and then discuss some future work. Okay, so that's the outline. So we're up to part one. And by the way, if anyone has any questions, just sort of interrupt me and ask them. I don't have an eye on the chat, so I won't be looking at that So if anyone has a question, just sort of interrupt, and I'm happy to answer that as we go. Okay, so part one. So cofunctors, if you've sort of only recently heard of them, might have some idea that they're a recent notion. And I guess this is still true, but really where they come back to is back in the 90s. So Higgins and Mackenzie first introduced this notion of not cofunctor, but they call it a comorphism. And they define this between Lie groupoids, and as well as a bunch of other notions. But for us, the important thing is that Lie groupoids are really just special kinds of categories. So they're groupoids, or particular kinds of groupoids internal to some category of smooth manifolds. Okay, and so here's just how they define comorphisms of Lie groupoids. And you'll notice actually one thing that'll be important later is they actually define a comorphism in two parts. They define it as some kind of action morphism and some kind of base preserving morphism. And you can see that this is actually a span of such morphisms. And we'll see this come up again later. And then sort of 4 years later, Aguiar defines, I guess, a more general notion of cofunctor. And in particular, he defines this two categories, cofunctors, and some kind of transformation between them. And he does this all in some very general internal setting in the monoidal category. Okay, and so here's some picture of how he sort of compares functors and cofunctors. Functors are sort of pushing morphisms in the direction of the object assignment, and cofunctors are sort of lifting them up. And we'll see this again later. So that's some basic original history. And then sort of 20 years later, that's not saying there wasn't any work done on cofunctors or comorphisms in that 20 years, but we come to this result of Arman and Uslu, who show that the polynomial comonads on set are the same as categories, and their morphisms are exactly cofunctors. And so this is a really interesting result because it's completely different to how both Higgins, Mackenzie, and Aguiar first sort of envisioned what cofunctors are about. And so we sort of see them in this different setting of well, I mean, stated here in terms of polynomials, but they were working in the language of containers and directed containers. And then since then, I guess there's sort of been a sort of increased interest, I suppose you would say, towards understanding cofunctors and looking at them in different settings and so on. And so in the last sort of 3 to 4 years, there's been work by Richard Garner and Robin Cockett and Bob Perret, David Spivak and Nelson New, Matthew Demeglio, and a bunch of other people that don't fit on the slide. And so I guess, yeah, there's been lots of work based on this characterization of cofunctors as morphisms of polynomial comonads. And so this polynomial perspective I won't really be talking much about in this talk going forward, but if you are interested in that perspective, there's this really great textbook, still in a draft form, by Spivak and New, which contains an account of this perspective of cofunctors. Okay, so that's some history and context. And I should actually, I guess, now tell you what a cofunctor is. And so what's a cofunctor between categories? Also a cofunctor, we write it as this pair, F and phi, A to B. What's it consist of? Well, it's an object assignment from the objects of A to the objects of B, together with this lifting operation. And so what this lifting operation does is it says, well, for every object in A, use our object assignment to give us an object F of A in B, and look at a morphism out of F of A. And what this lifting operation does is it says, well, let's take this data and output a chosen lift, which we call phi of AU. Okay, and this morphism lies above U in the sense that its domain and codomain lie above F of A and B with respect to the object assignment. Okay, so that's the basic data of what a cofunctor is. And so this lifting assignment has to satisfy some equations, and you don't really need to read those. What you just need to understand is that the lifting assignment preserves identities. So if this U is an identity morphism, it lifts to an identity morphism. And if we have a composite of morphisms, then that's the lift is the composite of the lifts of those things individually. Okay, so that's what a cofunctor is. Cofunctors are nice. We can compose them in a strictly associative way. So if we have two cofunctors like this from A to B and from B to C, we can just compose their object assignments because they're just functions. And if we want to produce a composite lift, well, we first go down all the way to the codomain, we lift it up one step, and then we lift it up another step, and that will be our composite lifting operation. Okay. And so we get this category, which David Spivak calls cat sharp. And this is the category of small categories and cofunctors. Okay. And so these are the kinds of morphisms that we're going to be talking about. Okay. So what are some examples of cofunctors? So the main example for me, I think, perhaps the most interesting is that every split op vibration, so we're all fairly familiar with op vibrations, and if we make a choice of lifts for an op vibration, it's called a split op vibration. And actually this splitting is actually a cofunctor because it's in a strict sense, so it's not just a cleaving, it's a splitting, and so every split op vibration has an underlying cofunctor. So that's one example. Another example is that any cofunctor between codiscrete categories or chaotic categories, categories where there's exactly a unique morphism between each object, are precisely very well behaved lenses. Okay, so many people might be familiar with this kind of what a very well behaved lens is. It's just a classical one that satisfies the three lens laws. Another example is that actually this category cat sharp is a fully faithful functor from monoids, from the category monoids op. So what that means is that every monoid homomorphism going from B to A is precisely a cofunctor going from A to B. Okay, and this is fully faithful. So all the cofunctors between monoids are just monoid homomorphisms. And here we can sort of see what's happening. We've only got one object. When we consider monoids as categories, and we push it down to the one object, there's no choice there. For every morphism coming out, we can lift it up to a morphism phi of u, which is what the monoid homomorphism is doing. Okay, but a little bit more general, the monoid homomorphisms, every actually bijective on objects functor from B to A is a bijective on objects, or we call it a bijective on objects cofunctor in the opposite direction. So this example of monoid homomorphisms is a special case of these bijective on objects cofunctors. Every discrete op vibration is a cofunctor in the same direction. And so these are cofunctors where this choice of lifts is actually unique. There's actually no choice at all, but there's a unique lift for every A and for every U. And finally, I guess this is a very specific example. That is, if we have a category, we have a cofunctor to the monoid of natural numbers under addition, then what this cofunctor is specifying is actually a choice of morphism out of each object in A. So if we have an object A, this cofunctor lifting operation is a choice of morphism out of each object A. So it's sort of like giving you some dynamics for your category in the sense that we're seeing how to push forward objects in our category and giving a choice of that for each object. Okay, so there's some very basic examples of cofunctors. And so one of the important things is, so we saw here that bijective on objects functors and discrete op vibrations are both examples of cofunctors. And actually they're both very special examples of cofunctors is because together they give an orthogonal factorization system on this category cat sharp of cofunctors. So every cofunctor factorizes into a bijective on objects cofunctor followed by a discrete op vibration. And so, for instance, if we have a cofunctor given here from A to B, so this is just sort of the information I showed you before, the little picture. How does the factorization work? Well, it factorizes like this. So the image, I guess, of the factorization is this category, which I call lambda. And it has the same objects as A. That's the bijection objects part. But the morphisms are now just pairs of an A and a U. And so going up this first step here, you can see that for every A and for every U, there's a unique pair, A and U, which gives us our discrete operation. And going up again, we can see that we're just applying phi to this pair AU to give a bijective on objects functor. And so turning this bijective on objects cofunctor around it to view it as a bijective on objects functor, we see that every cofunctor is actually equivalent to some span of functors. So this is really nice. We can use functors to understand cofunctors in this way. And so you might think, oh, well, why am I telling you about this orthogonal factorization system? You know, lots of categories have lots of different orthogonal factorization systems. So what distinguishes this one for the category cat sharp? And the distinguishing feature is that it actually has this nice special universal property, which says that, which is not just a property of the orthogonal factorization system, it's something additional. And so it says that for every cofunctor from A to B, and for every span of functors between A and B like so, if we have these two basic conditions satisfied, then there actually is a unique cofunctor into this category lambda. Sorry, a unique functor into this category lambda that we have here, which commutes with this factorization. So, so it's this really nice universal property, this orthogonal factorization system, and we'll see later in a few slides how this comes up again very naturally in the context of a double category perspective on cofunctors. Okay, so that's just some basic introduction. So that's the end of part two, end of part one. So I guess I'll just pause here briefly if anyone has questions so far. Okay, so part two, I want to talk about a double category cofunctors. And so I guess to talk about double category of cofunctors, I should first sort of briefly recall some stuff about double categories. And so what is a double category? Well, it's a two-dimensional categorical structure, so not too dissimilar from a two category. And what it consists of is a collection of objects, a collection of horizontal morphisms, which we draw like this, a collection of vertical morphisms, which we usually draw with the slash through, and a collection of cells, which are arranged in this way. And so the horizontal direction of composition in identities are all strict, but in the vertical direction, the composition is only associative up to isomorphism. So you can think of this as sort of like a two category in the horizontal direction and like a bi category in the vertical direction, if you're familiar with those things. Okay, and so that's, I guess, a very explicit way of viewing a double category. A more another way of looking at double category is that it's a pseudo internal category in the category of categories. So we have some diagram here, which is representing an internal category. And what we have is D0, which is a category whose objects are the objects of our double category and whose morphisms are the horizontal morphisms of our double category. We also have this category D1, whose objects are the vertical morphisms of our double category and whose morphisms are the cells of our double category. And the rest of this data, the rest of these functors, satisfying some equations for an internal category, gives us, tells us everything, all the information of the double category. And both of these perspectives are really useful. So sometimes it's very useful to study double categories as internal categories in CAT, and other times it's more useful to study them in a more explicit way like this. And what else did I want to say here? So a double category is flat if these cells are actually determined by their boundary. And so this is just something that, some terminology that I'll need for later. Okay, so it's sort of like if it's locally pre-ordered. If we have a boundary, double category is flat if that boundary either is giving a cell or it's not giving a cell. Okay, so that's what double categories are. And so I guess one of the key things I want to talk about is that once we construct this double category cofunctors in the next slide, it has lots of nice properties. And so what are some of these properties that we can talk about for double categories? I guess one of the most basic ones is that if we have a horizontal morphism in a double category, we can talk about its companion. So it's like viewing a horizontal morphism as a vertical morphism. And so this is called the companion of F if there are pairs of cells like so, satisfying some pasting equations. So if we paste this heart next to the diamond, we get the identity on F. If we paste it in the vertical direction, we get the identity on F lower star. So they're companions, and lots of things, lots of times when you have a double category, you want to ask what the companions are, and it turns out they tend to be quite nice. The dual of a companion is a conjoint, and so again, I won't go through the whole thing, but it's sort of saying, well, if we have a morphism, horizontal morphism from A to B, a conjoint is a vertical morphism in the opposite direction. Again, together with a bunch of cells, a pair of cells satisfying some similar pasting conditions. And so if a double category has all companions and conjoints, we sometimes call this a framed bicategory, if you're familiar with that language. Okay, so they're just some basic properties. We can talk about tabulators. And so a tabulator is a property of a vertical morphism in a double category. And it basically says, well, for every vertical morphism, we can associate some cell of this form. So we've got an identity here, a pair of horizontal morphisms and some cell, which is universal among such cells. So if we have any other cell of this form, where this might be some morphism H and K and some other cell, some other object here, then there's some unique factorization into this cell here. So tabulators are a special kind of double limit, I suppose you would say, for a double category. And if we have tabulators, we can even talk about strong tabulators, which is if we take this cell here and we paste it on the top with this cell for a conjoint, and we paste it on the bottom with this cell heart for a companion. If this pasting of cells is invertible, it's a horizontal, it's an isomorphism for all morphisms, then we say our double category has strong tabulators. And this is actually a very strong property. What it's saying is that every vertical morphism in our double category can be factorized into essentially a companion followed by a conjoint in a universal way. Okay, so they're just some properties of double categories. And so how can we sort of see, coming back to one of our main questions, which is how can we sort of see the duality between functors and cofunctors, or what's the right setting to study functors and cofunctors together? We can make this definition. So if we have a square of functors and cofunctors, so we have the functors going horizontally and the cofunctors going vertically, we say this square is compatible if it satisfies two conditions. The first condition says that, well, we have a commuting square at the level of objects. Okay, so applying H and then applying the object assignment of G, it's the same as applying the object assignment of F followed by the functor K on objects. So it commutes on objects, and the second condition is really saying commutes on morphisms. And so what that means is that we start with any morphism in B, we lift it by our cofunctor phi, and we push it forward by H. That's the same as pushing it forward by K and then lifting it via our cofunctor gamma. Okay, so we call such squares compatible. And so, okay, that's nice. We can define this category whose objects are cofunctors now and whose morphisms are these compatible squares. Okay, so this would be a morphism HK from this cofunctor FV to this cofunctor G gamma. Okay, and so something that's nice about these compatible squares is that we can actually sort of reinterpret them as diagrams of functors. And so one of the results I talked about before is seeing cofunctors as spans of functors. We can actually reinterpret these diagrams as commuting diagrams of functors where this lambda is from the factorization that I talked about before. And this unique functor between the lambdas is induced by this universal property that I was talking about. So the universal property for lambda for the cofunctor G gamma. Okay, and so really this is the way of taking cells of functors and cofunctors to these diagrams of functors. And so you can probably see where this is going. We can actually use this to define a double category, which I'm calling Cof, this blackboard bold C. And so it's this double category, and it's represented by this. This is the internal category representation of this category. So it's category of objects and horizontal morphisms is cat. Its category of vertical morphisms and cells is Cof, which is what I've defined here. Okay. And so I guess at the moment you might say, well, okay, you've just taken functors and cofunctors and put them together to make up some arbitrary double category. And I guess the point of the next part of the talk is to show that this is not really arbitrary at all, but it's actually coming from some higher categorical level. But for here, we're just working with it. So, and so one might ask, well, what kind of properties does this double category have? Well, it's flat. So this double category of categories, functors in the horizontal direction, cofunctors in the vertical direction, these compatible squares as cells. What are some of its properties? Well, its companions are exactly the discrete vibrations. So the example that we looked at before. Its conjoints are the bijective objects functors. It has tabulators. And so its tabulator is exactly this category lambda that we constructed from the orthogonal factorization system before. And actually the fact that these tabulators are strong is what's giving us this active, this orthogonal factorization system. It says that every vertical morphism, so every cofunctor, is factorized uniquely into a into a conjoint followed by a companion. Okay, so these things that we sort of talk about, I guess, that you can notice in an ad hoc fashion, and you think, well, these are really nice properties, actually also come up very, very naturally when we look at it from the perspective of this double category. So they're just some of the properties. Some other properties which I didn't talk about on the other slide, but still quite interesting, is that this double category of cofunctors is what one would call span representable, which means there's some fully faithful double functor into the double category of spans in cat. Okay, and so if I just go back to the previous slide, this is more or less what this representation of the cells is giving us. This is the output of that fully faithful functor to span of cat. And this is really nice because it means that we can study cofunctors more or less using entirely diagrammatic methods with categories and functors. So that's another property. If we look at the internal category perspective of this double category of cofunctors, we have a bunch of other nice properties. So these three functors in the middle are what we start with. We can show, for instance, that its identity map of this double category is fully faithful. We can show that its domain map of the internal category has a left adjoint, and its codomain map has a right adjoint. And this is what gives you, I guess, the unique cofunctor from a discrete category and the unique cofunctor, sorry, into a codiscrete category. The codomain map for the double category, so this cod from cof to cat, which takes every cofunctor to its codomain, is actually a bifibration, which is really nice. And moreover, its fibers have all finite limits. So we can do, these are very nice properties of cofunctors, which only really become apparent when we look at it from the perspective of this double category. Okay, And so we get to this stage and we might ask, well, what is the general framework for all of this theory that we can develop for this double category of categories, cofunctors and compatible functors, cofunctors and compatible squares. And so that's what I want to talk about in part 3. But again, I'll just pause here for a moment in case there are any questions. Okay, I'll keep going. So part 3, cofunctors as monad morphisms with examples. So here's where we sort of, I guess, change our perspective from looking at cofunctors as morphisms of polynomial comonads, and instead look at them as certain kinds of morphisms of monads. And so how do we do that? And so sorry, I should also apologize. This section is a little bit more theory heavy than the talk so far. And so you don't really need to understand all of this to understand the main point of the talk, but some people like theory, so I'm showing it. And so you're probably familiar with monads on categories, and many people are probably also familiar with monads in a 2 category. Okay, so this is the formal theory of monads due to Ross Street. And it turns out we can actually sort of do this in the double category as well. And at the basic level, the definition of monad in a double category is very similar to, almost identical to the definition of a monad in a 2 category. So we have an object in our double category A. We have some vertical endomorphism in our double category, and we have some cells which behave like the unit of the monad and the multiplication of our monad. And these satisfy basically the usual axioms for monads. And so this, I should also say that monads and double categories is not due to me, it's due to Gambino, Koch, and Fiore, I think are the authors of the paper, Monads and Double Categories. So that's what a vertical monad is. One of the nice things about double categories, though, and looking at monads and double categories, is that the monad maps are more natural. And so what do I mean by that? Well, monad map is a pair. It's a morphism, horizontal morphism between the object of our monad together with some cell like this. And it satisfies some compatibility axioms with our unit of each monad and the multiplication of each monad, as you would expect. But whereas when we look at monad morphisms in the bicategory setting, they don't always give us what we want. When we look at them in the double category setting, they do give us what we want. So what do I mean by that? Well, if we look at the example of the double category of sets, functions, and spans of functions, the monads in this double category are precisely categories, and the monad maps in the double category sense are precisely functors. So this is one of the benefits of using the monads in double category theory rather than monads in a 2 category or a bicategory setting. Okay, so that's categories and functors. And so you're probably wondering, well, where are the cofunctors going to come from? And so, as it turns out, if we're studying monads in double categories, we have the definition of monad, we have a definition of monad map in one direction, but because we're working in the double category, we can also look at monad maps in the vertical direction as well. And so what we get is this notion of vertical monad map, which utilizes the vertical information in our double category. And so I won't go through all the details. It's really just, instead of taking a horizontal morphism, we take a vertical morphism now as our thing that's moving between the monads, and we take a cell like this, and again, it satisfies some compatibility with our unit and multiplication maps. And so all up, what we get is putting this all together. I haven't told you what the cells are, but they're not so interesting. But putting this all together, what we can do is start with any double category we like and construct this new double category MND of D, whose objects are monads, whose morphisms in the horizontal direction are monad maps, whose morphisms in the vertical direction are these vertical monad maps. Okay, and whose cells are again, flat. They're determined by the boundary, I think. Okay, so that's all nice. And so we can ask a question of these vertical monad maps, which is, what if we require this vertical morphism of our vertical monad map to be a conjoint or a companion? Okay, so these are both very natural kinds of things in the setting of double categories. They're actually dual to each other. So if we look at companions, they're dual to conjoints and so on. So we can ask, well, what if we restrict our monad maps to conjoints or companions? And well, for one of these, the answer is quite boring. If we restrict it to conjoints, then these vertical monad maps are actually just equivalent to monad maps in the horizontal direction. So they don't give us anything new. They just give us back the simple thing that we looked at on this previous slide here. Okay. So that's that. And so actually, the way you can phrase this is that this double category M and D has conjoints, and the conjoint of a monad map in the horizontal direction is a vertical monad map with this conjoint here. Anyway, so but the question is, well, what about companions? Well, companions aren't giving us anything what we had previously, but we can just define them to be something. We can say, well, the monad maps are going to be what we get when we substitute in a conjoint. If we substitute in a companion, let's call that a monad retro map. And so this terminology is sort of coming from Bob Perret, who studied retro cells and double categories. Okay, so we can define this notion of monad retro map to be a vertical monad map whose F here is a companion. And we can restrict this double category that we constructed to what I'm calling M and D ret of D. So it's just a full double subcategory on the vertical morphisms whose on these monad retro maps here. Okay, so far this all seems like a very natural kind of thing to do. We saw that monad maps give us something boring. We saw that monad retro maps give us something which isn't something we are familiar with, but is completely dual. So we can see these monad retro maps as dual to the monad maps. We construct this new double category. Now, I guess one of the main punchlines is that when we substitute in the double category D is equal to span, then this M and D ret of D is precisely this double category of cofunctors that we constructed in part 2. So really, I should highlight this and make it more significant, because it's sort of one of the main reasons why this double category of cofunctors is such a natural object to study, and why functors and cofunctors come up very nicely via the same duality as conjoints and companions, is because when we substitute in span here, we get our monads, our categories, our monad maps of functors, and our vertical morphisms, which are these monad retro maps, are our cofunctors. Okay. And so we have this technology which spits out cofunctors when we put in this particular double category. And we want to ask ourselves, well, what if we put in other double categories? What is it going to spit out for us? And so we can play around with that. So for instance, if we define the double category of spans in a category not in set, but in a category C with pullbacks, we can define that here. And maybe a slight alteration is that if we have a monad which is pullback preserving and Cartesian, then we can define a double category of spans where the vertical morphisms are not just spans now, but they're T-spans. So we've applied our monad to the domain of our span. And an example here is when T is the list monad on set. Okay, so these are 2 double categories that were defined. And when we put in span of C to this construction, we get out internal categories, internal functors, and internal cofunctors. So we've just sort of generalized functors from cofunctors just by changing what double category we're instantiating in. And so examples of this are, well, the comorphisms between Lie groupoids are exactly the internal cofunctors when C is the category of manifolds and smooth maps between them. And if we do this for D's span with span CT, where C is set and T is the list monad, well, our monads now are multi-categories, and our retro maps are the cofunctors between multi-categories. So we can take any list of objects now, push it down to a list of objects under our object assignment and look at a multi-map out of that list, and the cofunctor between them sort of lifts that to a multi-map as shown here. So here we get internal cofunctors and we get cofunctors between multi-categories. We can also, just looking at the time, I'm running out of time, so I'll go through these a bit more quickly. But if we look in the enriched setting, again, we can construct for any distributive monoidal category V, we can construct a double category whose objects and horizontal morphisms are sets and functions, and whose vertical morphisms are what we call V matrices. So if we look at A and B as discrete categories, we can look at functors into V, and that's a V matrix. We can define some cells as natural transformations. And again, when we instantiate this construction, and we look at our monad retro maps in this double category of matrices, we get precisely enriched cofunctors out. And so in some more detail, what's an enriched cofunctor? Well, if we have enriched categories A and B, enriched cofunctor is a function between its collection of objects, and for each A and for each B, some lifting operation, which is a morphism in V, given by this HOM object here, going to a sum now. So this is where we're using the co-products in our monoidal category to this sum of HOM objects here, where we're summing over all of the objects X in the fiber of our object assignment over B. Okay, so there's some technical details here, but the point is that we don't have to sort of come up with this definition from scratch and define all these details and figure them out blindly. We sort of just get this from the general theory of double categories and works out all the details for us. And so a recent example are these weighted cofunctors, where V is weighted sets in this paper by Paolo Perrone in October last year. I'm going to skip over this because it's not so interesting. But if we want to look at some properties of monad retro maps, before we looked at a bunch of properties of this double category of cofunctors, I want to ask, well, how many of these sort of carry over to this more general level? It turns out several of them. So if D is some unit pure, so that just means its identity map is fully faithful. Double category with companions, which are needed to define these retromonad maps. Then we can see that our MND ret is also a flat double category. We can see that the conjoints are ones where this map here between the objects of our monads is invertible. Our companions are ones where a certain cell is an isomorphism, so it's sort of mirroring how we see bijective and objects functors here, and how we see discrete vibrations here in the ordinary setting. But a bunch of other properties are kind of really hard to talk about at this level. So we want to talk about tabulators in this MND ret. It's really hard to sort of compute what they are in general by putting some conditions on D. And so I have some conjecture, which is that if D is strongly span representable, then MND ret has tabulators, but I haven't really proven this in general. Although in some specific cases, we can see that if D is span C, yes, we have tabulators. If it's mat V, then we have tabulators if V is extensive, and if it's this other thing, we don't know. Okay, so they're just some properties of what we can understand from this double category of monad retro maps at this more general level. And then finally, in part 4, I just want to talk about some applications of what I've used this theory of cofunctors for in some other work. A lot of these applications are towards understanding this notion of delta lens. And so a delta lens is a compatible functor and cofunctor pair. Again, this is some Armin and Uslu first came up with this sort of characterization of what a delta lens should be. And we think, well, we've got functors and cofunctors, how can we see this in terms of our double category? Well, it turns out that a lens from A to B is just a particular kind of cell in our double category of cofunctors. So we look at a cell like this, where this horizontal morphism here is an identity and this vertical morphism here is an identity. Then the compatibility requirements of the cells give us precisely the compatibility requirements for this pair to be a delta lens. Some other property of double categories that I didn't talk about before is that double category is right connected if its internal identity map is right adjoint to its internal codomain map. And something, this black box that I came up with, which is a functor, takes any double category and spits out its right connected completion as a double category. And it turns out that when we apply this functor to the double category cofunctors, we get precisely the double category of delta lenses out. We can also show that the forgetful functor of lenses to cofunctors is comonadic, which again is a really nice property. It means that we can define some comonad on cofunctors whose co-algebras are precisely the delta lenses. So here I've just got a little picture of what a co-free lens is on a cofunctor. And finally, if we apply this right connected completion construction to MND ret of D, we can talk about lenses between monads in a double category more generally. And we can also get out, internal lenses and enriched lenses and so on, all just from this construction here. Okay, and so just to finish off, I want to quickly mention some questions that I don't know answers to yet. And so I guess there's more questions about, what other properties does this double category inherit from D? We can ask, well, I've talked about maybe 3 or 4 examples of double categories D where we look at our monad retro maps and we get something interesting. I guess there's the question of what are the other examples can we look at? There's this question of one of the first things I talked about in terms of cofunctors is representing them as spans. And this double category cofunctors is what we call span representable. And there's this question of, which I've already made, I guess, a bit of progress towards, but I didn't have time to feature it in this talk, is how much can we understand about cofunctors just from their representation as spans? And then there's also a question of how we can link all this back to polynomials and this theory of cofunctors as morphisms of polynomial comonads. And I think there's still some work to do here. And I'll skip over that. So just to wrap up everything in the talk, what have we done? Well, we've introduced some general framework for the theory of cofunctors with this double category, MND ret of D, of monads, monad maps, and monad retro maps, which works for any double category D with companions. We saw that this provides a setting when D is span, and provides a setting for looking at the duality between functors and cofunctors. So we can study them together in this double category COF. And we also saw that this double category has lots of interesting properties that one can look at further. And finally, we saw how we can use this general setting to study cofunctors in other more general settings, such as internal categories and rich categories and so on, and how we can use this to study delta lenses. And so that's, I think, all I wanted to say, and so I'll finish here. Thank you.